Welcome, everyone. This talk is about Lucene, Solr, Spatial in 2015, hence the talk title. Thank you very much for coming. I'm sure there are other interesting talks. I hate picking between interesting talks that I want to be at all of them. At least the videos are going to be online eventually. And I'm going to post this on SlideShare as well shortly. Quickly about me. Basically, I'm a freelancer in the area of Lucene, Solr, consulting. I wrote a book on it. I'm a committer, and that's kind of the important thing. So kind of the main areas that I like, the subject matters that I like within Lucene Solr a lot is obviously spatial. I've been doing stuff with highlighting lately. Say maybe 10% of my time is like spatial stuff. I do lots of just search stuff in general. I really like spatial topic in particular. Talk to me later if you're interested in my services. This year, what I want to say right off the bat here is that there was a sort of a hit by a bus syndrome you may have heard of, where only one guy knows most of the stuff, and if something were to happen, there's some risk in the health of an open source project. That was kind of a concern, but it's not really a concern anymore, because this year, there's really a lot to talk about, and a lot of the things I'm going to mention are things that I didn't do myself. I'm used to presenting my stuff, knowing it top to bottom. So I'm going to describe a lot of things going on. I looked into how many of these things worked that these folks worked on. So if we look across the stack, there's an open source library called Spatial for J, used by both Lucene and Solr for some of the spatial capability. I worked on those things. Ryan helped on Spatial for J side as well. I think Justin de Oliveira is in the room, helped with some of the GeoJSON stuff there. Mike McCandless and Nick Nice from elastic.com, they helped with some of the Lucene, the newer stuff on the Lucene side. And as well as Carl Wright from Nokia. And Ishan helped for some of the Solr stuff as well. Yeah. So as I looked at all the stuff going on in 2015, there's a lot going on. So I organized this presentation in terms of what are new features, capabilities, something you can do now that you could not do before, or at least not without custom code that doesn't really count, because you have to really address what the platform doesn't provide. So what can you do new? And then some new approaches that doesn't give you a new capability, but it's just a new way to do what you could do before that's probably faster and more efficient and kind of moving the state of the art. Everybody wants faster, better, leaner, all that good stuff. And then there's some improvements to existing capability that don't really, maybe add some smaller features. And I have a pending slide as well. Most of my time will be on the first 2 points. This is not a spatial overview talk. I'm not going to mention stuff that's already been there. That's cool and interesting, because there's so much stuff that's happened in 2015. I wanted to let you all know what's happening in spatial since the last time I gave a spatial talk. And the last time like for example, in particular, I'm not going to mention really date range field, which is a new thing added last year. I'm mentioning it right now, so maybe I'm cheating. But you may have heard of interesting use cases for spatial involving time ranges and stuff like that about plotting. You may have seen an interesting slide on that, and that's now like officially supported in terms of indexing date ranges. I'm getting ahead of myself, so I'll plow right in. As far as questions go, actually feel free. Probably a little different. Usually I keep questions to the end, but this time I'm going to say, once I get past, say, Heatmaps or something, I'll look around, and if you raise your hand, feel free to raise your hand at that time, because if we were just talking about it, it might be a good time. We'll see how that works. I might just do one question then, and maybe more questions to the very end. So we'll see how that goes. Okay. So new features. This is a summary of them. Heatmaps is a big one. Geo3D is cool. I'm going to get into these in some more detail. I don't have a slide for the GeoJSON stuff. That's basically GeoJSON read and write support on the Spatial for J library. It's a simple API call to read and write Spatial for J shapes. If you're at the Lucene layer, you just need to know to call a simple method. There's not yet a Solr hook to call it. There's no adaptation there yet. That should be straightforward. I was just recently talking to Justin about possibly doing that, so we'll see. So let's go forward. Heatmaps. Thanks to Harvard University for funding my work on this. I put this under one name, just Heatmaps, because it's a nice simple word that suggests images like these. it might be more specifically named spatial grid faceting. So that's really what it is from a Solr perspective. You're faceting. You're getting counts. And it is spatial grid faceting. The counts are attached to a grid square on a 2D space. I just had a 2D space, and granted, these two pictures are on a 2D, but the underlying engine of what I was working on, actually, it's whatever it will also, there's something underlying it called a Prefix Tree facet counter that also works on a one-dimensional date range field for high-speed date faceting as well. That's not completely done. It's actually committed to trunk, but more work is needed there. And there's a Lucene layer and a Solr layer. And most of the code is at the Lucene layer. That's really where that's really where most of the work happens. And then the Lucene layer adds more. The Solr layer adds a distributed support and a bit more, and hooks into the Solr kind of stuff. And it's scalable and fast usually. I'll tell you where it starts to slow down and where it's fastest. So under the hood, how does it work? So first of all, it requires what's called a prefix tree strategy based Lucene field. In Lucene spatial module, there's a variety of what's called spatial strategies, because there's different ways to index spatial stuff, whether it's bounding boxes or whether it's point data. Even if you have point data, there's different ways to do it. So there's an abstraction called a spatial strategy. Today, I'm not giving an overview of the framework, but needless to say, there's multiple ways to do things. You have to use this particular one, which I often abbreviate to RPT for recursive prefix tree, and which is grid-based strategy. It indexes grid squares, basically. And basically, the algorithm it takes a region of interest that you want to generate grid counts for, and it enumerates them on disk in a row, skipping as needed, and accumulating counts. Okay. So it's similar. It's akin to if you're familiar with Solr faceting. There's a facet.method, and you can switch it. You can switch it to enum on a normal just terms faceting. So this is conceptually similar, but on spatial data. And it's also going right into the cells of interest based on the region that you're interested in doing the heat map on. And it also works not just on point data. You can actually index polygons and generate heat maps on that. There's some caveats there, because if you index a polygon that represents like the United States, and if you zoom in to the edge of the coastline, maybe you're going to get to a point where the grids, the level of detail has run out. So there's some best practices that some people have already used the heat maps have figured out is you probably want to filter out. They're really big. If I'm zoomed in really small, I probably want to filter out the big stuff. So I'm only looking at stuff that only gets so big. So that's kind of neat. And basically the computational complexity is basically it's pretty much the number of cells. So if you want a 10 by 10 heat map, that's basically 100. So that's the order. So the more detailed you want it, if you want something that's massive high resolution, then you're going to be some expense there. And there's also a depth factor, as a constant factor as well. So the more, if you've configured your RPT to go down to as detailed as, say, a meter is the lowest grid square, then that'll definitely be the fastest if you're down there. But if you're at the top of the world, you're looking at you want a heat map of the entire world, and you know that you have cell data that goes all the way down to a meter, that's going to be the slowest case. Okay. And it's not computational complexity of the number of docs. There is a similar-ish feature in Elasticsearch that's been around that fundamentally works on doc values, which is a per document thing. So if you're matching lots of data, and you might match thousands and thousands of documents, and if you want to generate a heat map, your computational complexity is how many docs did you match. This is not. I don't care how many docs you match. It really has to do with how many terms or how many grid squares there are. And the Solr layer will distribute this out to the shards and basically add the counts. That works pretty simple. And as fast as this is, it could be even faster. I have plans. It's not to say I know I'm going to be working on it. I don't know, but assuming someone wants me to make it faster, I have plans to kind of lay the prefix tree of grid squares out in a way that lends itself to doing this fast. Because right now, every grid square has its children after it, immediately after it, and then its children after that. It's like a depth first search kind of layout of all the cells. And that means that if you want a heat map of the entire world, every grid square means a fairly long seek amongst all the terms to finally get to the next one. But if the heat maps were the most important thing and heat map speed was the most important thing, then the layout would better be, all of a given resolution, all of those grid squares should be in a block together. That would be more ideal. So it could be better. So it's pretty easy to use on the Solr side. You basically need an RPT field, and you don't need to do, if you already have this, if you have Solr right now, if you already, as long as you have Solr 5.2, I think, or later, and if you have this RPT field, you don't need to reindex. That being said, if you're going to be doing heat maps, one of the fundamental limitations of this heat map capability is that you have a kind of a limited degree of specifying what the resolution of these grid squares are, because they're the same as the actual index grid squares. The grid squares aren't really sort of computed on demand. So we basically look at the query shape that you're interested in, whether it's the world or whether it's the state or whatever it may be, and it tries to figure out how which grid resolution are we going to show that's indexed on disk. So in other words, so if you have like a geohash-based prefix grid, then you have 32 grid squares beneath each one. But if you want more high fidelity choices as you zoom in and zoom out of the map, then you want like a quad tree, because that as opposed to geohash, which is 32. Now there's a prefix tree. You may have heard of the quad choice. Well, there's actually a new one called packed quad I would recommend for this purpose. And I also suggest looking at whatchamacallit. There's an option called geo equals true or false, which is a little confusing, but what that gets down to is whether your grid squares are going to look like squares or whether they might look like rectangles. So if you really want to make these pretty and nice, you might want to try and make them square as possible. But anyway, there's some tricks I don't want to get into right now. So querying is very easy. You say facet equals true, and now there's a facet.heatmap option. You specify the RPT field, and you specify the geometry of the region that you're interested in. In this case, this is the entire world, which is the slowest case, by the way. So it's basically, if the user has a map on the screen, then put the bounding box of that. It doesn't actually have to be a rectangle. It can actually be something else. And it will return, it could be a circle if you want to. And the heat map, the result back, by default, it's inst2D, which basically you get a two-dimensional array of integers. Very straightforward. In fact, you can see that in the response. Inst2D, whenever you have a full array that will be all zeros, there's an optimization where it just puts null, so you don't have to have all those zeros coming back, because it's quite often using heat maps where you just have no data in certain areas. It's just a 2D bunch of integers. There's also the PNG option, which will, in this case, you would see a base 64 representation of the PNG. So if you wanted high-resolution heat maps, JSON representation of all those integers is not going to be very compact. So the PNG is another option if you have some high-resolution heat maps. And the PNG is kind of interesting because I'm sort of abusing the PNG format to put integer data in it. Because you can specify PNG, 4-byte PNGs, and it will be lossless. It's a way of communicating the integers in a grid with compressing the data. It doesn't do that by default. You have to enable it. It's kind of fun to do that for the first time and finally visualize on the screen the whole world for geo names. And one thing that's really cool working in open source is that other people see your stuff and then build off of it and use it. That's one of the things I really, really like about working in open source, having my stuff get used. And when other people build layers on top of you, other people can use it. And so there's already 3 JavaScript Solr frameworks. I think these are all pretty small. I'd encourage you to try them out. There's not that much to them. You can probably learn a bit just by looking at the 3 of them. I really like Jack Reed's tutorial. I tweeted about the heat map feature coming out in January and stuff, and he did a nice little blog write-up. Says here's how we're going to use it. Here's how we're going to configure the field. In fact, for time purposes, I actually don't think I want to show it right now because of all the other features. This is not a heat map presentation. but it's an excellent tutorial that walks you through, including a animated GIF and showing the response times. And at least on the GeoNames data, he was getting something like, at its slowest of the entire world, it was like 400 milliseconds. But the moment he was getting into the state level kind of resolution, like the Solr response times were getting down to sub 100 milliseconds, sub 50, and the next thing you know, it was 20 milliseconds to generate the same size. But because it gets lower and lower and lower, more and more detailed, it gets faster and faster and faster. That's pretty cool. Any quick questions about heat maps before I continue? Okay, there's the other opportunity at the end if you think of them later. Geo3D. This is probably one of the other big cool things in 2015 for Spatial and Lucene land. So the name of this thing is very misleading. If I were to name it, it would, I don't know. I'm not sure what I would call it, but it wouldn't have 3D in the name because it suggests something that it's not. This is not a general purpose 3D spatial library. No. It's a surface of a sphere, and it's using geocentric coordinates. So the center of the Earth is 0, 0, 0, and it's the unit sphere, or technically the ellipsoid. We have support for that now. And so like the North Pole would be 0, 0, 1, for example. And basically, what's awesome about this is that this is hard to come by. Like out there, you can't just tell some developer, hey, can you whip this up? And you need to have math skills and computer science skills. So Carl Wright at Nokia did this work, and right now it's a very self-contained. It's actually a module in Lucene that where this code lives, and what do I say right now? And it's basic. So there's a point, there's a rectangle, there's a polygon shape, there's a buffered line string which represents a path on the surface of the sphere. Pretty cool, and there's also some fun distance calculations as well. So, and this is just to emphasize the point that the world, we use 2D maps, but the world is not 2D. We know that. And oftentimes you can get away with it, okay? But when you can get away with it if you just have point data and you're just doing point radius queries, that kind of stuff, or just doing lat-lon bounding box queries. Then you don't need Geo3D for those kind of stuff. But if you've got polygons, especially potentially big ones, especially potentially near the pole, projections kind of suck for these issues. And you can actually drive from Miami to Anchorage, not necessarily drive, it'll fly, and beneath you there'd be ground the entire way. But you wouldn't know that looking at a typical web map like this. So the curved line is actually straight in the real world of that map. So there's I say two really big main benefits, and a third one as well. The big one is that this is surface of a sphere. This is somewhat of a holy grail to finally have this capability. This is hard to find out there. It's easy to find 2D spatial libraries. There's a few big popular ones, but it's hard to find surface of sphere, and actually does surface of ellipsoid, which I think is pretty amazing. Because the Earth is not actually a sphere. It's close, but and so one benefit there inherently is that it's an accurate representation of the world. That's good. The other benefit, which was actually the motivator, as I understand it, for Carl doing this work, is that he did it for performance reasons. Because if all your data gets into geocentric coordinates, assuming you get it there, I mean, you originally might have lat-lons, but the moment if you store all your data as XYZ data, then there's no trigonometry once you're in this space. It's all multiply and add kind of stuff. And you can do point in polygon and point in circle. You can do point in circle with a few multiplies and a couple adds, and avoid the innocent-looking, however expensive, trigonometry functions on the math class. So that was actually the motivator here. Whether that's fully achieved here yet, there's some integration with Lucene that's necessary. I'll get that next slide. Yeah, there's a Lucene-spatial 3D jar file now. There's a module for it. That's where it is. And there's some limited integration with the rest of the rest of the stack. And right now, if you want to try it, you basically have two choices. You can, on the sort of Lucene spatial module / spatial for J side, there's basically one simple class that wraps a Geo3D geometry into the shape abstraction, and then you can use the RPT field type with that. and you can index those things. You can index either points, you can index polygons, you can index whatever you want, and you get the benefit of the inherent 3D shape that you really want to index. And you can query by any of those Geo 3D shapes as well. There's also a Geo 3D Point Field that is based on other work I'll get to very shortly called BKD indices. That's probably much faster. I haven't seen benchmarks yet. And yeah, it's more, a couple of these things are kind of more in progress. The left side is not in progress. There's more work to do. The left one works. The right one, I think, has more potential, and a lot of it's been done, but I think there's more tuning to be done as well. Moving on, the other, I think, one of the third, say, big feature this year is accurately storing the geometries for more advanced spatial use cases into Lucene and Solr. In the past, this slide basically shows that you can represent a point in a fairly accurate manner using a grid technique, because you just need to add more. You just need to see D, DR, DRT, DRT2, DRT2Y up there on the slide. That's zooming further into Boston using a geohashed technique. But you can get more and more accuracy just by adding characters. That works fine. But if you want to represent a polygon, that approach just doesn't scale if you want to accurately represent the region, because you start needing an exponential number of cells. So if you have more advanced, if you're a user that wants to store polygons and not just polygons, but any other line strings or other that kind of data in Lucene Solr, it was fundamentally, it was putting it in there, but it was the index had a fuzzy representation of that shape, which was kind of, it wasn't ideal for many people. So what I've worked on, and I kind of announced this last year, that this is on the horizon, just a matter of time, and the time has come, that I basically married two existing spatial strategies. I've already mentioned RPT. SDV was done last year. That's serialized doc values. All that does is it actually stores the geometry, the points, the raw data for that geometry in Lucene doc values. But what's needed, though, is to marry those things together so that you kind of get the best of both worlds. So you get the index of the RP tree, the grid, but that gives you a lot of speed. But you really want to make sure that you accurately match the shape or not. And that's where the SDV comes in. So you marrying those things together, you get a lot of benefits, especially for the most common predicate intersects. By far, most people want to say, I want to index this data. Here's my query shape. Show me any kind of overlap whatsoever of my index data with this query shape. So that is specifically optimized to actually avoid. Without this optimization, things are potentially slower, because you can do one index. Now I'm also going to double check my matches against the geometry. That would be extra. But what I can do is I can detect that all of the hits you got are in inside grid squares to your shape. So I'm confident that they're all matches. I don't need to double check with the geometry. And that led to a very large 80% faster intersect queries. I was very, very pleased with that. And it led to a smaller index overall, because now I don't need super detailed grid squares to fuzzy represent my shape. I can play a trade-off between how accurate I want my grid and how much performance I get between the trade-off and index size and stuff. So this is basically going forward. If you have polygons, line strings, any of that kind of data that you want to put in Lucene or Solr, definitely use composite spatial strategy. On the Solr side, that's known as RPT with geometry. And it is compatible with the Heatmap feature as well, because it's basically two strategies in one, and one of those is RPT based. A lot of that Solr adapter is actually a Solr cache. That's kind of an add-on bonus, where it will keep a cache number of those things in memory. That's per segment. So those were the kind of the new features, things that you could not do before, basically. Now I'm going to cover a couple things that these are new approaches to things that you can do before, things that are more efficient or just do things differently. Both of these were done or had involvement with, I think, Nick Nyes or Michael McCandless. So there's a research paper out there on a spatial index called a BKD tree. I don't know how old that the paper is or whatever, but anyway, so a big thing I want to point out here is that to date, all spatial support has been using Lucene's core foundational capabilities. So what that what that has, so that means that if you want to index, you basically have a terms index. So if you want to try and do, tree-like stuff, you basically have to use a prefix tree, otherwise known as a trie. And then you leverage all that Lucene has underneath that to make that fast. Even though it wasn't designed for spatial purposes. You're sort of, I wouldn't say it's an abuse, but it is what it is. But there are spatial trees designed to be spatial trees from the get-go that are not bound by kind of Lucene's API constructs about how this works. So what Mike McCandless has done with this is that he basically read the paper, wrote some Java code that implements the BKD tree, but because Lucene doesn't have an API support for that, he had to kind of work around it. There's some work in progress to potentially add this as a Lucene core API, actually. So instead of just terms and doc values and term vectors and norms, you could actually have something in the future where I don't know what it might be called. Maybe it's BKD tree, maybe it's number multi. I don't know what it's going to be called. Who knows? I was just exchanging an email with him the other day. It is point data only. It has some limited use cases, but these are the vast majority of use cases for spatial, actually. Unless you're putting putting polygons in the index is one thing. I can use this for this. But most people have point data, basically. So this covers a variety of use cases. And it's pretty fast. There are, unfortunately, multiple implementations of this BKD tree. And most of them are in the spatial, the sandbox module right now, actually. And so there's a one-dimensional one, two-dimensional one, three-dimensional one. I have 3 slides for each of those coming up. And it's in progress. I'm not going to say the code doesn't work at all. It's tested very well. I'm very impressed with the testing that's there. And if you're interested in just getting more and more performance, I recommend trying it right now, knowing that the code might move around a little bit. The APIs might change a little bit. But a lot of the hard work's already been done, and it's there, and it's tested. They may not have some of the query support that you may want, but it's very impressive. Unfortunately, there are these 3 implementations. What's most likely going to happen is that there's going to be the ND support 6825 to Lucene core in progress. Once Lucene core has a fundamental capability to store these BKD trees of n dimensionality, then these 3 duplicate code bases, triplicate, that are conceptually the same but share no code will be able to use the same underlying backend, assuming that performance hasn't lost. But all 3 of those are using BKD concepts. Again, there's no code reuse right now. That's why it's in sandbox largely as well. Okay. So the one-dimensional one, basically this is an alternative for storing numbers. Lucene already has a way to store numbers, but this is another way. The benchmark I saw on it is that indexing takes longer. I don't know if it was 2x or something like that for the given number field, but it could be something like that. But query speed was like 48% faster, something like that. So there's a trade-off there. So this won't necessarily be for everybody going forward, depending on how you want to, what's most important to you. Yeah, it's basically an alternative to number fields. And it does multi-valued as well. And you basically, to use this, you basically need to use the range tree doc values format, and then you put your numbers in doc values. And it's actually not even limited to numbers. You can use this for bytes, and it puts the, I don't want to get into too many details, but if you had like an IPv6 scenario, you could do search for that with this. So the 2-dimensional one is BKD Point Field. It seems to perform awesome. I forget exactly where the benchmark is lately, but things are moving along. It might be better than 5.7x. I don't know. I also don't know if I forget what assumptions were made in that. But this, again, this looks very fast. And I think the indices are much smaller than the the grid-based indices. And there's the bounding box, the polygon. The circle is not quite there yet. That's in progress. There's a bug to be figured out. Yeah. And that's the end of the BKD stuff. Right now, if you were to look for it, basically all three of those implementations, just backing up before we get ready, all three of those implementations, again, because this is implementing stuff that there's no core Lucene API for, there's sort of a trick where it's a custom doc values format that doesn't actually do doc values. Those queries cast the doc values field they get back to be a special one that manages the on-disk kind of stuff. So it's sort of a hack around Lucene's APIs because Lucene's underlying APIs don't have a way to do this yet. Okay. Okay. GeoPointField. So this is, Nick Nyes has worked a lot on this. And this is basically an alternative to some of the GeoHash RPT tech. This is, it's doing some similar things. And I think part of the purpose is to have one kind of easy to use, one field that's more simple and internally has some complexity to do what it's doing quickly. And, but it's doing something that's conceptually similar to what RPT is doing. So there are grid squares, and it also stores the data into doc values as well. And it has a nice, efficient second pass. First it uses the grid squares to get to some region, and then it uses doc values to double check which documents are in the region of interest. I think there's, next slide, more details. Yeah. Hold on, sorry. I am impressed with how the API is internally structured. It reuses a fair amount of Lucene, Lucene's existing multi-term query logic. I rather liked that in this. I don't have a benchmark for you. I even asked Nick last night, and he just couldn't find it. So many JIRA comments, and I don't know what the latest is. But again, these things are moving forward, and it's got much faster a month ago or something. So what is needed in all of this is like a bake-off, a performance bake-off. That'd be great. But some of these things are moving. It's a little too early to maybe even have that benchmark yet. So this is a new approach. It doesn't have anything to do with any of the spatial prefix tree, spatial for J stuff, none of that. For better and worse, there's no, if you had a custom shape, I've done some custom shape stuff, and this doesn't work with that yet. Although it could be made to, but it doesn't. It has no dependencies. I think that's a value proposition that was behind why part of its existence anyway. There's no Solr support yet, and it's fairly easy to use. And yeah, there's like one line of code for adding the GeoPoint, and use one of those few query types to query it. Yeah. So improvements. I don't have detailed slides on this because I'm trying to make sure I get all this material into one presentation. But I want to highlight kind of maybe one or two things in particular. So probably the biggest thing here that I think was awesome is that if you're storing non-point data into Solr, like polygons, et cetera, the indices are much smaller now. I think it was 33% smaller index, and to my surprise, that resulted in 68% faster, 44% faster queries and 68% faster indexing. So that was a huge win for those people that have, again, non-point data in their index. And it didn't change the index format. It just emitted fewer terms to represent the shape in question. And I just adjusted the queries to be mindful that certain terms it was expecting aren't there. So that was a big win. And the packed quad prefix tree in particular, I think I already mentioned that earlier. I mentioned Heatmaps, and I made a suggestion of using prefix tree equals packed quad, because I think this packed quad implementation is really tight and lean and a good choice. A couple other things I'll mention are that Ishan has been working on the Solr side, and I think in January we got some convenience units support to Solr, Even simple things like that take time because of backwards compatibility. And there's some nicer spatial query parsers that are designed to make it look a little bit more like the, I forget what spec you'd call it, but if you've ever used relational databases and spatial support in those databases, you've seen a bunch of queries that start with st underscore like intersects or whatever. We want to add some query parsers that have that same kind of flavor to make it look a little bit more familiar to those that know that, and just to be a little more nicer in general. So some pending to-dos, that's kind of a big overview of all the stuff going on this year. And from that is sometimes you work on new features come out, and that suggests more features to use to use those. So if you come up with a new way of indexing data, well, then you need a Solr adapter ideally and other things. So that's what some of the to-dos are. By putting it here, I'm not saying that I'm necessarily promising to get them done, or these are things on my radar, or I'm aware of that other people are working on that are interesting. Yeah, 2015 isn't over yet. And that's it. But any questions before I? Yeah. So that's interesting. By default, what you do is you give it a query shape, like the entire world, or maybe somewhere we're zoomed in. That's your screen, and you specify it has a default. It has a certain default, and what I recommend doing is what it doesn't, and you can explicitly tell it, I want this zoom, this, what's it called? This is like the grid level. I think it's called grid level as a parameter, like facet.heatmap.grid level equals blah. But the thing is, how do you know what number is the right number to do it? So practically speaking, what I suggest is try it for a bit and zoom in, zoom out, do a lot of zooming in, zooming out to get a sense of what the resolution is, and then you can tweak another parameter that tries to figure out what resolution to choose. Because the trade-off with this style of heat map is that it's limited to the index grid squares, which are predetermined at index time. So I can't just simply have a parameter that says I want the grid squares to be exactly like a yay big, because you don't have control of that. So there are a couple parameters that allow you to that try and use less or more, and I just think it's a little bit of experimentation, of playing around with it. And when you get the response back, it tells you what the grid level is. So if you wanted a button on the screen that says increase resolution, you can hit that button, and you could next time you do a request, you could just use the next higher grid level number. Another thing I wanted to mention about the heat map stuff that I didn't mention in the beginning is that it's also useful for point plotting purposes. The two examples in the beginning where we're all kind of very summary level gradients. But if you ask for a very, very, very high density heat map, at that point it's not really a heat map anymore. It's putting your dots on the map. And I've worked in scenarios where, instead of the top 10, you want to show everything. And who knows what everything is? Maybe everything is 10 things, or maybe it's so dense it looks like that. So you can do very high density heat maps as well. Like I'm talking close to the resolution of your maps window, which is 1,000, whatever it is. And they'll use a lot of memory, but at that point you're talking point plotting use case. I wanted to mention that as well. And that's it, right? No, one more. Okay. I've been asked that before. No, you get a count. I have been asked before, what if there was some other field, like a value that represented, I don't know what, I don't know, salaries of people working in that area. And wouldn't it be nice to sort of like take the average of that, and I want to use that. I don't care how many things I have there. I want to know the average of a direct values field. No, that'd be something that could potentially be added. There is no support for that right now. Related to that kind of mindset is that I don't think I mentioned, is that you can, in one request to Solr, just like you can do facet on multiple fields, you may know that you can even facet on Solr on the same fields multiple ways. So you could facet, you could do a spatial facet, what do I want to say is you could do heat map faceting on the same grid data, but by specifying different filter queries, and then you're trying to get a difference. So you might have one filter query that represents a time range, and another filter query that represents a different time range. And you might want to show a heat map that represents the difference of how your data is changing from this time bucket to the next time bucket. You can send one request to Solr that does 2 heat maps on the same data, which is pretty cool. I had plans of doing that at a much higher scale with a little slider window where you can move something on the slider on the screen, and imagine doing rapid heat maps. I didn't get time to do that project. But, OK, Steve? Conceptually, it's at the lowest level, it's a reusable thing. It doesn't even care about dimensionality, actually, because it uses the APIs. But then when you go layer up, so you could get there. It could potentially work. OK, cool. Thanks, everybody, for coming. I really appreciate it.